back, everybody. Now that you're an expert on dependent and independent variables, let's move on and get into some of the more nitty-gritty of the different types of data there are out there. Let's get started. Our lovely overview. We're going to start with the idea of measurement and how we measure things. First, we have to conceptualize, then we operationalize. We're going to talk about the difference between qualitative versus quantitative data. We're going to look at variables and different data types, a few examples, and then I'll show you different data types in R. So measurement. We're going to measure some variables, but what's a variable again? Let's check in. A variable is any characteristic, number, or quantity that can be measured or counted. A variable may also be called a data item or an element in the data set. Age, sex, business, income and expenses, country of birth, capital expenditures, class grades, eye color, vehicle type are just some examples of variables. There are countless others. So now that we kind of know what a variable is, just anything that you can measure, let's think about measuring some of these things. How about how tall are you? That one's fairly easy. I'm about 5'6", so about 66 inches. What is your class rank? You could look on your transcript maybe to see that. How much do you weigh? Get on a scale. How old are you from your date of birth? And how many formal years of education have you had? This is easy enough, right? Maybe you would just have to specify a few things like, do you want to know in kilograms or in pounds? Do you want to know in inches, centimeters, feet, things like that. But now, what about here? Give me a measurement here. How intelligent are you? How creative are you? How confident are you? How happy are you? How statistically literate are you? How would you go about measuring these sorts of things that are a bit more conceptual than just measuring your height? With your height, you can just use this tape measure. But how would you measure someone's intelligence? So first off, what are the concepts of these things? Before we can even measure it, we have to kind of define what these things mean. What does it mean to be intelligent or creative or confident or happy? And what constitutes statistical literacy? Take a moment to think about this yourself. How would you go about trying to measure these different concepts? So the first thing you have to do when you're trying to research and measure something is you have to conceptualize this particular concept. It's the defining of your variable of interest and ideas into a concrete definition and construct, thus enabling you to convey your idea and your particular concept, what it means to you to other people. Because what you think of as intelligence or creativity may not be somebody else's definition of that. So it's very important that your terms are explicitly stated so a person knows what you mean, at least, when you say intelligence or creativity. Here are some examples. I found these online. These are reasonable definitions for each of these concepts, but it can vary because, for example, intelligence, here it says is the ability to acquire and apply knowledge. But some people also talk about intelligence like kinesthetic intelligence, that is like dancers being aware of where their body is in space. Or emotional intelligence, being able to read other people's emotions, being able to keep your own in check. There are many different types. And that's okay as long as you conceptualize and define your terms to begin with. All right, so you've conceptualized your concept. Now what do we do? How do we go from this concept that you've so beautifully defined through conceptualization and make it into something measurable? What steps do you need to take and what questions do you need to ask? Think about it for a second. Give yourself a moment. I'll wait. All right, ready? All right, the next step is called operationalization. It's a process of defining the measurement of a phenomena that is not directly measurable, defining what is and what is not part of that concept. Operationalization is not just a hard word to say, it is the refining of your concept to a level of clarity that you can measure it. Next is operationalization. It's the process of defining the measurement of a phenomena that is not directly measurable, defining what is and what is not part of that concept. So operationalization is the defining of your concept to a level of clarity that you can measure it. So how would we go about measuring something like creativity? This is a brick, obviously. What can you do with this brick? List as many creative things as you can think of in 1 minute. Be creative. Pause me and go. All right, we're back. Did you write them all down for 1 minute? Did you count them all up? Cool. I hope you did. If not, looking at you. So how would you go about scoring this task? You could go back and maybe count all of the unique things that you wrote, but if you had, let's say, 10 and your friend had 5, does that make you twice as creative as them? What if instead you had 5 answers and your friend had 10, but your 5 answers were really unique, really creative, and really different, and their 10 answers were kind of typical and normal? I've given out this little example for the last few years to many, many different types of people, and I've always been amused by the different things that some people come up with. Some of the more common ones are you can build a house or a road out of it. One of the most common but brow-raising answers is you can throw it through a window, or you can tie a note around it and throw it through a window. But I would say one of the most creative I've heard is that somebody said you could cover the brick in a layer of frosting, put candles in the holes, and present it to somebody as a birthday cake and a prank. Would you score that higher? And just for the record, I don't have any right answers to this. This is an example of how when researchers want to go out and research something as big and as vast as creativity, they have to figure out creative ways to measure them. Time to operate. Let's think of a few different ways that we can conceptualize and operationalize some of these things. Health, anxiety, extroversion, personal space, type A personality, statistical literacy. You pick one and try to conceptualize and operationalize it. Pause me. All right. So hopefully you took a moment. This is an example of taking something very conceptual and very personal, a person's idea of their own personal space, and turning it into something we can actually measure. So here is where the person is, and this is their personal space. Then we have like intimate space, social space, and public space. Now, another interesting note about this great diagram, which they've now quantified, now we can actually measure that if somebody is about right here, they're in my intimate space. If somebody's here, you are way up in my bubble. Move, step off. But what else is important to know about this? It's important to know where the researcher conducted this research, because different cultures have very different ideas of what is personal space and public space. Some cultures are a lot more close and intimate than others. Now let's say that you were going to go and try to study this idea of personal space. You could go up to people and say, hey, can you describe your own idea of personal space? Or you could ask them where their idea of personal space begins, with like a measuring tape. Now, what is the difference between these two questions? This leads us beautifully into quality or quantity. Which will it be? So show me the data. There's 2 main types of data that we can categorize them in, like we can lump them into 2 main things. We can talk about qualitative data, which is like the quality of something, and quantitative data, the quantity of something. What is the main difference between those? Let's have a look at this. What is this? Describe it and measure it somehow. Take a second. Go. All right, did you come up with anything? So you could say a few things about this. You could describe it as a portrait with a woman with a thorn necklace and some animals around her. The thorns are piercing her neck and it's dripping a little bit of blood. She looks very solemn and it feels kind of intense, right? These are all great qualitative descriptors of this painting. Or we can be a little bit more quantitative with it and say it was painted in 1940. These are its dimensions in centimeters, and maybe it took a certain amount of hours to paint. But I don't know that, sadly. I wish I did. And this is, of course, by Frida Kahlo. This is actually in the Harry Ransom Center on campus that maybe we can all go visit again one day. Anyway, what's the main difference between these 2 types of descriptors? We have one that is very full of descriptive words and phrases, when this one is restricted more to numbers. And that is the main difference between qualitative and quantitative types of data. So qualitative is rich about human information and behavior, also imbued with feelings. You can think of it as like observations and interviews with people. You can analyze themes, like what are the most common thoughts and feelings about the pandemic right now and how it's affecting your well-being. But unfortunately, things like that can be hard to analyze and to quantify and reproduce. Alternatively, you could use something like quantitative data, where we have concrete numbers. Things are measurable and usually easier to reproduce. You can run statistics and perform analyses on the numbers. You can summarize things and test things. If I wanted to know how COVID was affecting your well-being, I could ask you to write me a short paragraph, which would be rich in human behavior and information, and it would be qualitative in nature. Or I could create a small survey or a scale with maybe 1 through 5. How do you feel about COVID-19 right now? And you would rank it, and I would then have a whole bunch of numbers to play with afterward. So now we're going to look at variables and data types. You might be wondering, if we already looked at independent and dependent variables, why is there more? Well, a dependent and independent variable can be measured in different ways depending on what kind of data that variable is. We'll see some examples here. Variables can either be qualitative or quantitative in nature. Qualitative variables are usually called categorical variables, and there are different types of those, such as nominal, ordinal, and binary, which we will discuss shortly. If something is a quantitative variable, it can either be discrete or continuous, and it can be either interval or ratio under that. We're going to talk about all these now. Qualitative or categorical data includes the nominal and ordinal, also binary, but we're going to focus on these two. And quantitative involves discrete or continuous, and they can be either interval or ratio type data. Here's another flowchart I found online that's basically reiterating what I showed you in the previous slides. All right, let's start with qualitative categorical types of data. So what's in a name? A rose by any other name still smells so sweet. Anyway, so nominal data is purely a name or a category. Nominal, nombre if you know Spanish, it's just a name or a label. It's qualitative in nature, and it's limited for the kind of math that you can do on it. Many times it's like a grouping variable. So everybody with brown hair over here, everybody with blonde hair over here, and everybody with red hair over here. And some gray hair people over there too. You can assign numbers to these kind of categories. If I had males and females, for example, instead of writing into a computer program male, female, usually we reduce it to zeros and ones. Now this does not mean that a male is worth 0 and a female is worth 1, and it doesn't make sense to subtract one female from one male and get a -1. That wouldn't actually mean anything. They're really just labels, but we're using digits as these labels. You're limited in the type of mathematical operations you can do on them, but one thing that you can do is add up how many times you saw ones or zeros, and you'll know how many females and how many males were in the group. Here's a little table with a few different examples of some types of data. And now I'm looking for the examples of nominal data, which is basically like valueless numbers. The numbers don't really mean anything. They're just labels. So which of these three, we have subject ID, we have gender, and we have age. Which of these would be considered a nominal type of variable? Let's look at age. Do you think age is something that is just a label? Being 15 is just a label? Not really. That's actually measurable from the day that you were born, how many years have passed in 15. Now, gender, as I just said in the last example, we could say that we have a male, a female, and a male. These are not actual numbers per se. They don't have value. They're just labels, and just simplified labels. It makes computer operations and things like that easier. So let's look at subject ID now. We have 103, 345, 430, and 957. Do these numbers actually have value? Is this person 957 points of something? No. These numbers are also just labels. They're basically, instead of a person's name, you just have an ID number instead. So both of these, subject ID and gender, are examples of nominal data. So here are some examples of a bunch of nominal and categorical data. The list goes on and on. You could come up with hundreds of these. So a few could be gender, favorite color, ethnicity, your political affiliation, your particular opinion on X, whether you're right or left-handed, your religious affiliation, the type of fidget that you normally engage in. I'm a big fan of fidgeting. Your college major, your car model, your geographical location in space right now, as far as a city name, your favorite food, music interests, Netflix preferences, the language that you speak, and whether something is true or false. The list goes on and on. Now, one of the things you can do with nominal data is create a frequency distribution. So a frequency distribution is the number of times a certain categorical variable is observed or somebody responds with that answer. And it's a count of the number of people in that certain category. So let's say I went out and asked a few people what their favorite color was. We have brown, black, white, blue, purple, etc., etc. And let's say that 2 people said brown, 6 people said black, 1 person said white. So we would just tally them all up and then just get the frequency. Now, another thing we can do with that frequency distribution is also get the relative frequencies. So we have the same information here, but I just rearrange them till we have the highest and to the lowest. We take the number 18. 18 people said that red was their favorite color. But what is the relative frequency of that response? So we take 18 divided by the total number, and we get 0.24, which is the proportion, or 24%. What does that mean? 24% of all the people I asked said that they like red. And so on. We can say purple is 23%, 16% of people like blue, 15% of people like orange, etc. So this is the raw rate or frequency, and this is the relative frequency. You just take that particular answer's total count and divide by the total number of people that you asked. So there's another thing we can do with the relative frequency is to get the probability of something based on our data set here. Based on the data that we have available to us, what is the probability that I ask someone what their favorite color is and they say red? In this case, based again on this sample that we took, there is a 24% chance that the person's favorite color is red. So see, the relative frequency will also tell us the probability of something, again, based on this particular data set at least. So here is a nice little visualization, and this is one thing that you can do with nominal and categorical types of data. Here on the x-axis, we have all the different types of categories that nominal variable can take. So we have all the different colors that we're at least allowing people to pick from. And on this one over here, we have a frequency bar graph that here we actually just have the raw count and the raw number. So remember, 18 people said they liked red. Now, this chart looks basically exactly the same. It has the exact same message and the exact same shape. But now we're talking about relative frequency. So remember that 24% of our sample said red. Here they are. 0.24 is the relative frequency. Relative to all the other possible color choices, red was 0.24. All right, get in order. First, second, third. Now we're going to be looking at ordinal data, which is the next level. This tells you about the rank and order and things that can be sorted. But ordinal data will tell you the rank and order of a data set, but it does not tell you the difference in those increments. So for example, I could put everybody lined up by height in this class, 6 feet apart for social distancing, and we know that the tallest person is taller than everybody else, the second tallest person is taller than everybody below them, etc. But we don't know how much of a difference in height there is between all the people. So if we look here, let's say that our first person is like 6'7", something really, really tall. The next person might be 6 foot, so there's 7 inches of difference between the tallest and the next tallest, but then subsequent people, there's only about an inch of difference between them. So this length, this difference here, the amount of difference from person to person is not the same size. Another way to say that is the intervals are not equal. This interval here is not the same size as this interval here. Or in this example with runners, we know when they stand on the podium, we know who's first, second, and third. We know who was the fastest and who was the third fastest, but we don't know the time difference between them. So if we look here, the person in first place has quite a bit of a lead on the other two, but then the next two people who are going to be second and third, the difference between them is much smaller, and the difference between third and fourth might be even smaller. So again, ordinal data, it does let you know the order of everybody, but it does not tell you how much of a difference there is between each person. Likert scales are a very common tool used in social sciences. You've probably answered a few things like this where the choices are from strongly disagree or strongly agree, things like that. Now this is technically considered ordinal data because we know that they are in order from agreement to disagreement, but we don't actually know if the space from here to here is like really as strong as the space from here to here. Because maybe you moderately to neutral, that's like a little step, but then like if you strongly agree, it seems like you're going a lot further out than just one little side step. So even though they're technically ordinal, many times in social science research they treat them as interval data, which is the next one we're going to use, because interval data you can do math and some statistical operations on. So if ever I ask you what kind of scale Likert scales are, I actually want you to say interval, but you should impress your future teachers and say it's technically ordinal, but do it respectfully. So here's some more examples of ordinal data, something like your school rank, percentile rank, hotness rank. I feel like people used to do that. Your hotness rank, your famousness rank, creativeness rank, Likert scales technically, socioeconomic status like high, medium, and low when you organize it that way, or your level of agreement like strongly agree, strongly disagree, stuff like that. There are many, many others out there. So now we're going to move into the quantitative data, which can either be discrete or continuous. And this is the kind of data we can do a lot more of our statistical things to. The first thing we need to distinguish between is discrete versus continuous data. Now, discrete data has a fixed set number of options and finite number of choices. It can't be cut up into like halves or 3/4 or 0.0029. It is just 1, 2, 3, etc. So for example, the number of laptops or cell phones you own, you can only have a whole number of that. So 0 or 1 or 2. You can't have 1 and 0.89 cell phones. The number of cars you own or the number of significant others that you've had in the past. Those should be all whole number things. And continuous data, conversely, is an infinite number of values. The decimal level can just keep on refining, technically. You could put like 0.000000 and actually keep getting tighter and tighter and tighter. So if you can measure it and keep zooming in or keep cutting it more and more and more, it's probably continuous. So for example, age can be calculated to like an infinite level, like 33 years old, 1 month, 4 days, 7 hours, 12 minutes, 45 seconds, 120 milliseconds, etc., etc., etc. But many times we will make things into whole numbers. So instead of asking exactly how old you are, we just say that we are 33. Also, continuous variables can be discretized at the discretion of the researcher. So interval data can be discrete or continuous. Now, it's similar to ordinal in that all the increments are in order, but now the interval from one person to the next is the same. We can look at something like temperature. The temperature from, let's say, from 2 degrees to 3 degrees, that's 1 degree of difference, is the same size as from 92 to 93 degrees. There's a 1 little notch increment, and that's the same amount of degree change no matter where it is on the scale. But the ratio, so how many times a number can be contained in another number, between them are not meaningful. So what does that mean? That 80 degrees is not necessarily twice as hot as 40 degrees. That might seem a little bit obscure, but it's because interval data, this is one of the defining features of interval data, in addition to the equal intervals, is that it does not have a real zero. The zero is actually kind of made up or arbitrary for convenience. So if we look here, we have Celsius and Fahrenheit, we have 0 and 32. These two numbers correspond to something that's important to us, which is the freezing point of water, but is 0 in Celsius zero heat? The complete absence of heat? It might feel like it, especially if you're from Texas like me. That is just way too cold for me. But is that complete absence of heat? No, because think of Celsius as 0 is different from Fahrenheit 0. Fahrenheit 0 goes technically a bit lower. So the 0 is arbitrary with interval data. Some examples, so time as far as BC and AD, and I guess we don't really talk about it that same way, is an example of interval data because the 0, the start point, is technically arbitrary. It's not the beginning of time. There was time before the birth of Christ, so there was still time before that. Here are some more examples of interval data, like IQ scores. You technically cannot get a 0 on an IQ test, and the intervals between each IQ point, so from 100 to 101, is the same point value as 130 to 131. And things like the ACT, SAT, GRE, MCAT, LSAT, all those other horrible acronyms that people make you take to get into schools. Calendar year, as far as like 2020, because again, that 0 is arbitrary. The degrees of temperature, Likert scales, but again, they're technically ordinal, but we treat them as interval for mathematical reasons. And another example of interval data is ratio data, which we'll talk about in just a second, when it's converted into a standardized metric like a z-score, which we will talk about in a couple weeks. So ratio scale data, this is the last one. So this one has equal intervals, just like interval data. So for one point to the next is the same length, like 1 inch from 0 to 1 is 1 inch, 1 inch from 101 to 102 is still the same inch. Now the difference with ratio data though is now it does have a true 0. The 0 is no longer arbitrary. It's actually important and relevant. So here we have thermometers again. We have a Celsius here, but now we have this one over here with a K. Any of you hard scientists out there? This is the Kelvin scale. And Kelvin does have a true 0. In this case, it's not the point where we are very, very cold. It is the point where the motion of molecules stops. So it's the complete absence of heat. So that's why Kelvin, as far as temperature goes, is actually a ratio scale. So here are some examples of ratio data, such as a person's age, because there was a point where you did not exist, and I guess you could even count it since conception, but we're, you know, splitting hairs here. Your weight technically is ratio data. The income, years of education, minutes from a certain time, so the number of minutes since this video started. The hours that you study, the amount of time you spend doing a certain thing, the time since the Big Bang, so that would have a true 0, a true relevant 0. The number of miles driven, time with the 0 start point again, distance from a start point, or a family size. Sometimes you can feel a bit uncertain when you're trying to figure out what kind of data you're dealing with. Some scales of measurement are easier to distinguish from others. If someone were to ask the year, you could ask the year since when? Since birth? Since Anno Domini? Since the Big Bang? It depends. And I've even had to dispute with some of my own professors in graduate school about, I think the question was blood pressure? And I said, well, it sounds like ratio. There is a true 0. You did. So they did give me the points. And if ever you have a quiz question that you want to maybe dispute because you read the question a little bit differently, feel free to contact me. I'm open if you can defend your point. So some scales are also treated as different types of data when justified for certain purposes, like the ordinal scales, Likert scales that are treated as interval. So as with many things in life, it depends, and sometimes you can change things to suit your needs. So some clarifying questions that can kind of help you figure out what kind of data you're working with. So nominal questions typically start with something like what or which. So which one of these is your favorite color? And interval and ratio can seem quite similar. When trying to distinguish the two though, you can ask, can I have 0 of this particular thing? If you can't have 0, you would go with interval. Again, like intelligence, you cannot score a 0. Even the people who score the lowest still don't get a 0, unless you were in a completely vegetative state, which would be completely inappropriate to try to administer an IQ test to you then. The question is how much or how many of something might give you a clue that it is ratio or interval. So let's do some examples now and see if you can identify what kind of data we're dealing with. Let's start with this one. How many siblings do you have? Now let's not get too picky here about if you have some half siblings because your parents remarried. Let's just say that you can only have a whole number of a sibling. So first off, the clue about how many tells you that this is definitely a quantitative, so we can get rid of the categorical here. We know we're dealing with discrete or continuous, and in this case I'm saying don't split hairs about half siblings. You can only have a whole number, so in that case we know that it is then discrete. It's also ratio data because you can have 0 siblings. So with the scales again, frequently used psychological measurements, Likert scales, what level of measurement are they? As far as answering on a test question, should you answer nominal, ordinal, interval, or ratio? In this case, you would answer interval, but technically it's ordinal. So for the sake of any quizzes or something like that, answer interval, because that's how scientists usually treat it. But you know in your heart of hearts, it's actually ordinal. About intelligence tests. We've already talked a little bit about this. What's the level of measurement? Nominal, ordinal, interval, or ratio? So first off, we know it's not nominal because we have actual numbers here that do have some quantity associated with them. Now if you look from here, from 0 to 115, that is the same size, the same width here as over here from 85 to 15. It's a difference of 15 in those little intervals there. So we know that it's at least interval data, and if you're wondering, well, is it ratio? Remember, you cannot have 0 as a score on an IQ test. It stops here. And is it continuous, discrete, or categorical? We certainly know it's not categorical because we're dealing with numbers, but is it continuous or discrete? Now this one, I don't blame you for not immediately knowing, because unless you've taken an IQ test or have more experience with them, you wouldn't know that there are no decimal points with IQ tests. It's either 100, 105, 116, whatever it is. It's always a whole number, so in that case it is discrete. For our last example, these are called event-related potentials. So if you were doing some neuroscience and you wanted to test a person's reaction time to something, you could put the EEG on their head and maybe like make a noise with a buzzer, and they have to like click a button after they hear the noise. So in this case, we're talking about reaction time. The stimulus, remember, is delivered from a certain point, from a start point, and then you have to react, and they're going to measure how long that took. What kind of level of measurement is this? Nominal, ordinal, interval, or ratio? And are we dealing with continuous, discrete, or categorical? Well, the fact that we're dealing with time tells you that it's certainly not categorical. These are not just naming things. These are numbers. But now, is it continuous or discrete? And is it interval or ratio? So we can see here, this is a good clue. We have a 0. And that 0 is a real 0 because it's from a certain start point. So in that case, we're dealing with ratio data. And technically this is continuous because you can get more and more precise based on your instruments. So next up, now that we have a sense of the different types of data, now we can actually start diving into it and describing some of it. So I'll see you in that next one. And now, as promised, we're going to cover some of this in R. R is sensitive about the data that you put into it, and it knows that you can't run certain statistical operations on certain types of data. For example, if I had a whole column of male, female, male, male, female, 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 and I said, calculate the average, R, it would throw back an error, because how would you get an average of male, female in this situation? Even if I were to code them into zeros and ones, if we do it correctly, these will be coded as factors. And factors are basically categorical or nominal types of variables that have been recoded in some sort of way. Now it's actually possible to tell R to get the average, but what it's really going to give you is a proportion. So if you were to take the average of zeros and ones in this case, it'll give you, let's say it was half and half, then the average would be 0.5, which is 50% and 50%. But the important take home here for a second is that those numbers are not technically numerical in a sense. They are just more labels. Instead of using characters like the alphabet, we use digits as names now instead. So R also has its own way of classifying the different types of data, and we can look at what type of data it is by using the function class, which I'll show you in just a moment. So a continuous variable, remember, something that we can measure out to a certain decimal place. In R, that's called a numeric. And it can be any possible value with any number of digits. The next one is called an integer, and in this case, it can only be whole numbers. So it's basically like discrete data. And these are the two types of data that, again, you can do some mathematical operations on because it's appropriate. The other types, it's not appropriate to do so. The next important one is a factor, which I just mentioned, that it's taking different categories and saying this is category 1, category 2, category 3, and labeling them as such, like 1, 2, and 3. And the last type of data that's at least of interest to us right now are characters. And this is really just it's called a string sometimes. It's really just a word or a name. So let's look at an example here. You can check the type of data using the function class. So you would just type out CLASS with parentheses, and in that parenthesis, you put the data that you want to check. So here I'm loading in a data set. This is the Spotify Top 50 data set from 2019. And we can view it using this function, or I can click on it and you can see it kind of like in Excel. And we can also ask R using our class function. I use class and I type in the data set name. So in this case, I'm calling it Spotify Top 50. Then we use this $sign. And the $sign, what's going to do is pop up a little variable list of all the possible variables and all the columns that are in your data set. So here, I want to know, how is R treating the genre category? Genre is like pop or techno or reggaeton, whatever floats your boat. So we want to know, how is R treating this category? Did it treat it as a character, or is it treating it like a factor? Because right now, I want R to treat that as a factor. I want to know how many songs were pop songs, or how many songs, what's the frequency of pop songs, the frequency of electronic songs, etc. So this will spit out an answer, and it will say, at this point, it's treating it, unfortunately, like a character. So R read this in incorrectly. But that's okay. Sometimes we can change it to suit our needs. And we can also reassign them. So here I am taking the data set, that $sign, the variable I want, which in this case is genre. And I'm going to put that little arrow to assign something. I want you to turn into a factor. And this is another function that you type factor, parentheses, and you type the exact same thing, the data, the $sign, and the column variable that you want. And now R will transform that and treat it now as a factor. And we can check again to make sure using the class function, and now we're sure that it's treating it as a factor. So you can also look at the data another way using the little global environment interface that there is. Here you'll see the data, and it'll just usually be a straight across row. But if you click this little drop down right here, click it, and you will see all the different columns that are in your data set. These are all different variables. So here we have the track name, so it's the name of the song. And that one, because we don't expect any songs to have the same name, we can just treat that one as a character. We're not really going to look at that one. We just want to, it's just the name of that particular song. Then we have artist name. Now this one, it could be a character, or we can turn it into a factor. And in this case, in future examples, I do turn it into a factor because I'm curious, did any one musical artist have more than one top 50 hit in 2019? Basically, did any of them have a frequency greater than 1? Then we have genre, and here, this is before I changed it into a factor. We also have beats per minute and energy, loudness, etc. And all the rest of these, thankfully, are being treated either as integers or numeric. And what are those again? Integer is basically like discrete data, and numeric is basically continuous data. So what's important for us is that all these we can do statistical calculations on. And you can also, one last way to look at the data is you can click on, not the little blue drop down, but just click on the data set itself, or use that view function, and it'll pop this up, which basically is just like any sort of Excel kind of file where you can look at all of the columns and scroll through it. So that's all I have for you for now with R, but I do encourage you to go play around, load in this data set, and go see the different types of data, and see if you can change any of them using some of these functions I just showed you. All right, get ready for describing data in the next one. I'll see you there.